Okay, so let's dive into this. We're just going to continue on with the same homework that was done last time because it's due at the end of the day today, and he is not assigned a new homework. So unless anyone has some concrete questions about things that they've learned in class so far, does anyone have any questions about things that have been covered in class? I will take that as a no. Do people have specific questions that they want me to go over?
Could you talk about number 6, please?
Yeah, sure. I think I covered 6A last time. Did I?
I think so, but B and C would be helpful as well.
Okay. So the video for last week is posted on the same YouTube channel that I posted the first week on. So if you just search my name, it should pop up. But I'll dive into B and C and then ask if anyone has other questions and then possibly circle back to cover A again. Show that there are infinitely many positive integers d such that gd is equal to epsilon. So we have GA is equal to GB, and 1 second. So we have GA is equal to GB, and we can assume B is greater than A, right? Then B is equal to A plus KD, K being a positive integer, and all of these guys being positive integers. Right. So we then have G A equals G A plus KD. And what does that tell us? That tells us that GKD, that it's equal to this guy. And if we have GA times this thing is equal to GA, then what do we know about this thing? So this thing times GA is equal to GA. What do we know about it?
Just the identity.
The identity?
Yeah. Therefore, GKD is equal to the identity. So we can just actually, so now we have that it's equal to the identity for all of these guys, and therefore GKD equal to G to the D to the K is equal to the identity to the K is equal to the identity. So we have this for all K in the positive integers. Right? Does that make sense to you guys?
Yep.
Cool. So since the positive integers are well ordered, there is a smallest positive integer d star such that g to the d star is equal to epsilon. Find the upper bound for d star and justify that. So using a similar argument to what we used in 1, basically G has n elements. That means that if I multiply G times each of these n elements, it's because it's a group, it's going to give me a distinct new element for each of these, right? Which tells me that D star has to be less than n, right? Or less than or equal to n. Because I can only cycle through it so many times. At some point, I have to loop back due to the fact that G is closed, and that every time I multiply G by a new element, that is going to give me a new element. Does that make sense? Does that make sense? Justin, does that make sense?
Yes.
Cool. Do people have a next question that they want me to answer? So what did I do? Did I do 4 last time?
No, you didn't.
Okay, I'll do 4 for you guys then. Or give you guys some hints. So the below is an incomplete multiplication table for the group G. So there are only 2 groups that are of order 4. Klein 4, which can be represented as Z2 cross Z2. It's going to be isomorphic to that guy. And 1, 1. So this gives you 0, 0. This gives you 1, 1. So this is on addition, right? This is the equivalent of, actually, I guess it's also equivalent to multiplication piecewise, but I think it's a bit more natural to think of it in terms of addition. And then we get, oh no, it's not equivalent to multiplication. Ignore what I just said there. You guys know how to do addition mod 2, right? The other one is equivalent to just Z4. Oh, sorry, we should do 0, 1, 2, 3, 0, 1, 2, 3. So here, what do we see as the identity?
A.
Yeah, cool. So A is equal to the identity. And then what do we get? We get B plus B is going to be equal to C. So that should tell us which of these 2 groups I'm working with. Am I working with something that looks like Z4, or am I looking at something that looks like Klein 4?
Klein 4.
Not quite. So one of the special things about Klein-like groups is any element applied to itself, operate on itself, is the identity. Do we get that here?
No.
No, yeah. So we get B plus B is equal to C. So we can think of this as A is equal to 1, A is equal to 0, B is equal to 1, C is 1 plus 1, so that gives me 2, and then D would give me 3, right? Right?
Yeah.
Cool. So if we were to fill it in this whole chart, we would just get the equivalent of, so what we get 0, 1, 2, 3, and then we get 1, 2, 3, 0, and then we get 2, right? Yeah, 3, 0. And then here we get 0 and 1, 2. Cool. So it's going to look basically like that. You just sub in your symbols. You're dealing with A, B, C, D instead of 0, 1, 2, 3. Does that make sense? Does that make sense?
Yes.
Cool. So that should give you enough information to answer all of those questions right there. Do people have any other question that they want me to address? I believe I did both 1 and 2, right?
Yeah.
Yeah.
3, I think, should just be kind of computationally, but not conceptually hard. Is that correct?
Yeah.
Cool. 4 there. 5 I did, right? So
Yeah, we
so
did all of them.
Yeah, I think I've done all of them except for 3. And like I said, it's just kind of a lot of computations, but it shouldn't be that hard. So do people have other questions about broader course material? What have you guys covered this past week?
Do you have access to the next homework or no?
I do not. I wish I did, but sadly I do not. I think you'll be posting it very soon, but it would have been nice to be able to go over it today, but I think he wants to only have one homework out at a time.
Do you know if he plans to post answers afterwards once everything's graded?
Well, we haven't gotten around to grading homework 1 yet, but the answer key is up.
Oh, okay. Thanks.
Yeah. So I think we may have. I know I haven't done my grading yet. I don't think the other TA has done his grading yet, but we've assigned all of the grading, so that should be done by the end of the week for the first homework.
That's good to know. Thanks.
No questions about material that has been covered in class. What have you guys covered in class this week?
We did subgroups and generators.
Cool. Do people have any questions about those? Give me a subgroup of both Z4 and Klein 4. Hmm. Can't seem to write the Cayley tables correctly today. What is a subgroup of this?
I mean, the identity is always a subgroup.
Yeah, so we always have the trivial subgroup of just 0, or the identity here. We have one other pretty interesting subgroup, not terribly, but somewhat interesting. What is it? I mean, I guess we have 2 other subgroups because the group itself is always also a subgroup of itself, just like any set is a subset of itself. Hint, use a generator. Pick an element to be the generator. What happens if I pick 1 to be the generator of this function? Or of this subgroup? What do I get? Pedro, what do I get? Pedro? Okay. Lucy, what do I get?
Sorry, I don't know.
What happens if I pick 1? Does anyone know what a generator is?
Yes.
Cool, what is it?
It generates the entire group when you keep applying it to itself. So it basically it's when you apply repeated powers of itself, you generate the entire group.
Cool. So do any of these guys look like they would generate the entire group?
1 and 3.
Exactly. Because 1 to the 1 gives me 1, 1 to the 2 gives me 2, 1 to the 3 gives me 3, and 1 to the 4 gives me the identity 0. 3 also works because 3 to the 1 is equal to 3, 3 to the 2 is equal to 2, 3 to the 3 is equal to 1, and 3 to the 4 is equal to 0. Right? But I can also think of a generator for a proper subgroup. And in that case, 2 is going to be the more interesting one. I mean, technically, the identity will always give you this trivial subgroup, but 2 will give you 2 to the 1 is equal to 2, and 2 to the 0 is 2 to the 2 is equal to 0, which gives you this subgroup, right?
Yeah.
What about for Klein 4? What happens here? Is there any generator for the whole group? What did I say that the kind of interesting thing about Klein-like groups is? What did I say the interesting thing about Klein-like groups is? If I take any element and apply it to itself, I get the identity, right? So is anything going to be a generator for the whole group?
No.
Exactly. But it does tell me that each of these guys is going to generate a different proper subgroup, right? And I'll get 0, 1, and then 0, 0. This will be its own proper subgroup. Just 0, 0 will also be its own proper subgroup. 0, sorry, 1, 0, and 0, 0. That's its own proper subgroup, as is 1, 1, and 0, 0. That guy right there. All 4 of these are proper subgroups, and then we have the big group itself to get a 5th subgroup. Does that make sense? Also note, these guys are all isomorphic, right? They operate exactly like Z2. Does that make sense? What else did you guys cover? Have you guys done any infinite groups yet?
No, I mean, we have a class after this, so.
I thought you guys met in the mornings.
No.
No, we meet from 4 to 5.
Oh, okay. Well, if nobody has any questions, then I don't really know what else to cover. I will let you guys go, and I'll just stick around if people want to ask me questions in kind of a smaller setting. I'm going to stop recording.
Right, thank you.
Have a good one.